All right, so we're following the tentative schedule. Today, it's one lesson, but it's an important one. We're going to talk about binomial distributions today, which are very important, discrete distributions. You could argue they're even more important than uniform. So binomial distributions, very important discrete distributions. All right, that's the last lesson in part 2 of the course on discrete probability. Now, bear in mind that lessons 11 through 18, so we're ending part 2, right? Lessons 11 through 18. So that constitutes part 2. That's your second homework assignment. We're going to discuss it, take questions, talk about it on Wednesday. And we had a really good session last time for the first homework session. And then we'll go over the answers quickly next Monday, October 5th. But I think the class would agree that the previous session where we really talked about the homework, that helped a lot. Otherwise, Monday the 5th is going to go way too fast for you if you don't know what's going on. So make sure you enter next Monday knowing what's going on, okay? With just a few questions here and there. Okay, and the homework due date will be Tuesday, October 6th. And the whole month of October is going to be a big grading month for me. So I'm finally able to wrap back to spring's video. So I finally have some time for grading. All right, get that started. All right, so the homework for lessons 11 through 18, well, I'll be working on it at the end of this week and next week. So I'm hoping next week sometime. Well, yeah, that's very much on my mind. So in October, early October, yeah. All right, so anyway, the second homework will be due Tuesday, October 6th. All right. So again, you'll be getting a bunch of grades back in October. Okay, yeah, the fact that I don't have to make brand new videos, that's going to be a huge relief. September was video month. I'm proud of these videos, but man, they take a long time. They take a long, long time. All right, but I'm proud of what we got from those. Let's see, any questions before we start the videos? We're going to have a lot of fun today. Cards and coins, we'll have lots of fun today. The binomial distributions you see all over the place. All right, any questions? Any questions? Let's get started. We'll have lots of fun today.
Hi, everyone. Let's start lesson 18 on binomial distributions. How many successes and what are the chances? Actually, we're going to start this with a fun game. It's the Monty Hall problem, which comes from a famous game show from 40, 50 years ago. Here's Michael, our old friend Michael from Ding, to explain.
Okay, so you know what? I have a better copy of this video, and I don't have to stop the recording. I just can't monetize the video, which I had no intention of doing. I had no intention of making money off my videos. So given that I'm not monetizing the videos, I don't have to stop the recording. All right, here we go. Here's Michael again.
First of all, what is the Monty Hall problem? Well, it was named after game show host Monty Hall, who hosted Let's Make a Deal. One of the challenges he would put the audience to involved 3 doors on the stage. Door number 1, door number 2, and door number 3. Now, Monty would honestly tell the audience member that behind 2 of the 3 doors was a goat. A goat, yeah. But behind one of the doors was a bunch of money. Let's say $1 million. Now, the audience member got to pick one of the 3 doors. And if they picked the door that had money behind it, they would get to keep the money. But if they picked a door that had a goat behind it, well, they'd get a goat. And they'd have to take care of it and travel back home with it. And point is, you weren't supposed to want the goat, but goats are awesome. So I, in my version, have replaced the goats with pieces of poop. Fewer people want poop. Some still will, but the point is you're supposed to want the money. If you pick a door that has poop behind it, you have to, like the goat, take the poop home and take care of it and feed it, all that normal poop stuff. So here we go. There's money behind one door, and there's poop behind the other 2. Hannah, pick a door. Door 1. Okay, door 1. Awesome. Before I open door 1, I'm going to tell you this. It's good that you picked door number 1 because there's poop behind door number 2. You see that? There's some poop. Ooh, you don't want that. But now, Hannah, before I give you what's behind the door that you have chosen, I'm going to actually let you switch. You can switch to door number 3, or you can stick with your original choice. After you've done that, either you switch or not, you will have to take home whatever is behind the door that you have chosen. Would you like to switch or stick with your original choice?
Stick with my choice.
Why?
Because it doesn't matter.
It doesn't matter, right? It kind of feels like a 50-50, right? You know that there's no money behind door number 2, which means the money's either behind door number 1 or door number 3. So you have a 50-50 chance, right? I mean, why not just stick with your first choice? Because what if your first choice was right and you switched? Well, then you would really hate yourself for not going with your gut. It would feel like you had lost the money, like you had it and then you lost by switching. If it's behind the door you didn't pick, then it's like you just picked wrong. You don't feel like you're losing something. So psychologically, yes, most people decided not to switch.
Now what's he going to say? So now I'm going to go back to the main video here. We can skip over Michael now. I want to go to the applet. I discussed the applet as part of the video, the Rossmann Chance applet. And by the way, you should have gotten this in your email. If you haven't gotten this in your email, go to rossmannchance.com. Rossmann is after Alan Rossmann. I'll go back. This is rossmannchance.com. I met Alan Rossmann. Alan Rossmann. These are both Cal Poly San Luis Obispo instructors. Great stats team there. And Chance is named after a person, Professor Beth Chance, who did these applets. So now I emailed you the link, but if you go to the Rossmann Chance applet collection in the upper left, all right, Monty Hall is in the upper right. See here, probability. Monty Hall is the second link under probability, and you can click on that. Already have it, and I'll discuss it over here. So here in my video, I discuss it further.
Okay, so let's actually play this game for ourselves. This is a great applet from Rossmann and Chance. Let's drag this down here. So let's actually play this game. I'll do a couple of rounds and then you'll go ahead and play 18 of them on your own. Okay, so let's say that I want to pick door number 1. I just sense, my spidey sense says that the money or the car is behind this door. It's a car. That's the grand prize, I'm hoping. So let's open this door. It doesn't open the door for me right now, unfortunately, but what the game show host does, Monty Hall, he opens another door, which is this goat over here. We reveal a goat. Now, the idea is that I can either stay with my current door, door number 1, or I can switch over to this third door, door number 3. So let's say that we always employ a strategy of switching. We're going to play that game. We're going to employ a strategy of switching. So instead of staying on door number 1, I'm going to open up door number 3. Switch, and I win the car. And you can see that I register the win, and you see that dot there. I've won 100% of the time thus far. Let's try this again. Play again. All right, this time my spidey sensed that the car is behind door number 2. Open that, okay? And Monty Hall reveals to me that a goat is behind door number 3. Looks like kind of a satanic goat, huh? All right, so once again, I have a choice to either stay behind door number 2, or I can switch over to door number 1. Okay, I'll go ahead and switch to door number 1, and once again, I win the car. I'm 2 for 2, and that's registered over here. So here's what I'm going to do. I'm going to email this link to you, this Rossmann Chance applet, and go ahead and play 18 rounds. Play this 18 times, and you can pick whatever door you want at first, but promise me that when given the choice, you'll always make the choice to switch to the other door, like I did. So let's go ahead and stop here, and you play 18 rounds of this game, and let's see what proportion of the time you win and what proportion of the time you lose. Is it really 1/2, 1/2? So go ahead and play 18 rounds of this, and then come back to me at the next video.
Okay, so we're actually going to go ahead and do this, all right? So, so again, in case you forgot how to get here, right? Okay, go to rossmannchance.com, rossmannchance.com, named after the 2 professors who, well, Beth Chance really did the applets, all right? Alan's the guy who goes out and speaks to people. I saw him twice, once in real life, one by Zoom. Okay, go to the Rossmann Chance applet collection, okay, upper right, the second one, second link on the right under probability, Monty Hall, all right? And then the instructions are here. You can read the instructions, all right? But again, do what I did 18 times. Pick a door, always switch, all right? And then play again when you want to play again. And do this 18 times. And I want you to track Okay, now you're always going to be in the switch column. You're always going to be in the green because you're always going to apply the strategy of switching, okay? So your wins and your losses should total up to 18. I want you to play 18 rounds of this game, okay? Like for example, I picked door number 1. I switch. I must switch. Here, I win the car, right? And I register the win. Play again, okay? So do this 18 times. And in the chat, tell me how many times you win when you employ the switching strategy. Now remember, half of 18 is 9. Do you think you're going to get about 9? What do you think? Put the number of wins you get in the chat. All right. We have some fast people here. I see 12, 15, 13, 15, 12. I believe you folks. I believe you folks. 15, 12, 11, 14. Wow, it really looks like we should switch, huh? Oh, 9. Yeah, that's okay. That's okay. I expected a 9. 14, 12. Go another minute or so. So look at these numbers. Yeah, they don't like their measure of center, whether you take the mean or the median. I think it's going to be a fair bit higher than 12. What do you think? Or 9. It's going to be a fair bit higher than 9. It's more like 12. Yeah. 9 is half of 18. It's looking more like 12-ish, right? Yeah. In fact, yeah. You folks are getting a lot more than 12, actually. 10. Okay. And by the way, I've had students get like 5. It doesn't mean they did it wrong. It's just, sampling error. Oh, okay. That's kind of sad, though. I kind of wanted at least one person in single digits just to demonstrate sampling error. Okay. Okay, so I'll wait another 30 seconds. I think some people are still doing it. Okay, 9. Yeah. Yeah, I know we do. Yeah, we should get some people in single digits, right? 11, all right. Another 9, okay. But see, this was the point, right? I mean, if you really think that's a 50-50, you'd have thought, well, you'd have the center around 9. It doesn't look like 9 is the center. We had to struggle to get as low as 9, didn't we? The center was more like 12, right? There's a reason for that. Okay, so any more takers? I'll wait about 15 more seconds. All right. Yeah, but these numbers are very reasonable. So we got here a 12, 15, 13, 15. In fact, I may as well type them in now. Yeah, I'll go ahead and type it in a text file right now. So the results from our class, okay, we got 12, 15, 13, 15, 12, 15. Wow, 12, 11, 14, 10, 14, 12, 10, 12, 9, 11, 9. Yeah, it does not look like the center is 9. It looks like the center is more like 12. Yeah. All right, I'm going to put you people in for posterity. Monty results, F20. You're in the record books. Wow, what do you think, folks? I'll give you some time to think about that. Why does it seem like a 2/3 chance of winning, not a 1/2 chance? Because 12 is 2/3 of 18. Any thoughts about that? Give until 8:25 on my clock here. That's a factor, right? Because here's the deal. When I click on a door, Monty is never allowed to show you the car right off the bat. Otherwise, what's the point of the game? That's the point that Michael's going to give. That's a good point. Okay? Monty has information. Monty has information. Yeah. Any other ideas? All right. So let's continue. In fact, let's continue with Michael. He seems to be a wise guy. A wise guy. Here we go.
But mathematically, you should always switch. In fact, if you switch, You will win not half the time. It's not actually 50-50. If you switch, you will win 2/3 of the time. And if you don't switch, you only win 1/3 of the time. So you have a 66.6 repeating chance of winning if you switch. Why should that be? Why is it not 50-50? Well, it comes down to two extremely important facts about this problem. The first one is quite easy for us all to agree on. It's the fact that when you make your first choice, oh, by the way, I never actually showed you the result. You stuck with one. And Hannah, just like I said, you should have switched. You shouldn't always switch. Let's be clear about that. I'm not telling you a strategy to always win. I'm just telling you the best strategy in the long term. So you chose to stick with one, but there's poop behind one. The money was behind three. So there it is, $1 million to scale. So let's get back to these two important facts. The first is that when you first choose a door, the probability that you have chosen the money is 1 in 3. Okay, that's the chance that you'll be right. The money's behind one of 3 doors. You have a 1 in 3 chance of picking the door with money behind it right off the bat. That's pretty clear. But that also means that 2/3 of the time, you are choosing a door that does not have money behind it. More doors have poop behind them than have money behind them. The second and much more important fact is that the host knows which door the money is behind. And the host will never open a door that has money behind it. I believe most disagreements over the solution to the Monty Hall problem come from confusion over the rules of the game. So let's make them extremely clear. First, you pick a door. Next, the host opens one of the 2 doors you did not pick. And the door the host opens of those 2 will always be a door with a goat behind it. You are then asked if you would like to stick with your original choice or switch to the door that you didn't pick that the host also didn't open. This is why it feels like a 50-50. We know that the money is either behind the door you picked or the door that the host didn't open that you didn't pick. It's behind one of them.
See, here's the problem, folks. So there are 2 unopened doors. People just assume that's a uniform distribution, half-half, coin flip. They assume a uniform distribution. That's our nature. That's not the case here.
Definitely not behind the one the host opened. The host only ever opens a door with a goat behind it. But surprisingly, to switch or not is not a 50-50 choice. Switching allows you to win 2 out of 3 times. If you chose a door, like Hannah did, door number 1, say, and then the host flipped a coin and randomly opened one, sometimes the host would open a door that had the money behind it. And that would be terrible television because the money would be revealed and the host would say, okay, well, you were wrong. Would you like to switch to the one door that remains closed? Of course you wouldn't. It wouldn't matter. The game would be over and it would be boring. Instead, the host always opens a door of the 2 you haven't chosen that has poop behind it, okay? Or a goat, depending on which version you want to go with. So what does that mean? Well, it means that sometimes you choose the door that the money is behind. That's awesome. And in that case, it doesn't matter which door the host opens. The host could have a rule where they always open the, leftmost door, or maybe they just flip a coin and open 1 or 2. Either way, the host can open either door. But most of the time, you didn't pick the door the money is behind. 2/3 of the time, you pick incorrectly. In that case, the host is forced to open 1 door. The host has no choice. The host cannot open 3 because the money's behind that door. The host must open the other door to reveal the poop. This is why you actually have more information than you might think. The host is always avoiding the door with the money behind it.
Yeah. It's basically Let's Make a Deal problem. Who's hosting now? I think Wayne Brady may have done a recent incarnation of it, but Monty Hall was the old-time host from the 70s. Wayne Brady, yeah. Let's Make a Deal. Go ahead and go to YouTube. Now, unfortunately, their videos weren't closed captioned, so my ability to use them was kind of limited. But, all right. And here's another great explanation I found from Numberphile over here. Another great explanation.
We imagine not having 3 doors, but we imagine having 100 doors. And let's imagine that we're playing the same kind of game. We have Monty over here. He is going to give you an opportunity to pick a door, and your dream flashcards behind one of these 100 doors. but there are 99 zonks all behind the other doors. Now, what is it that you're going to do? Well, you're going to pick a door. Say again, you pick door number 1. Now you're feeling a little bit different than you might have felt in the case where there were 3 doors, because there you thought, wow, I've got a 1 in 3 chance. Here you're thinking, I've got a 1 in 100 chance. I'm not going to get that car. It's not behind door number 1. It's probably behind one of the other 99 doors. What Monty does is he opens 98 of those 99 doors. He shows you 98 zonks and he asks you, now, do you want to switch? Well, maybe just because of the sheer numbers, this thing is a little clearer. You know that there was 99 out of 100 chance that the car was over here. And now the only door you're left with after Monty shows you all those zonks is door, say, number 37. And you're thinking, this is no good, this is no good, all those doors are no good. Do I want to stay with 1 or do I want to stay with 37? You can sort of almost feel the concentration of that 99% going behind door number 37. And so you switch over here and very likely you're going to get that car.
That's our car, better than mine. Okay, so going back to my video, I think I basically play those videos. Right. Yeah. Again, it was good that with these videos, I checked the copyright. Basically, as long as I don't monetize my videos, I'm okay. But it's okay for me to play them. But sometimes on other things, it's not as good. Like you can't play them on mobile, like on cell phones. So I got to watch out for that. Okay, but I didn't have to stop the recording here. Yeah, in my video 2, I basically played the videos. Yeah, and I showed a little clip here from 21.
An interesting video from Numberphile over here. So a 2 in 3 chance of winning if you switch. By the way, this problem was famously featured in the film 21, Kevin Spacey there, explaining the Monty Hall problem. So it's a very famous problem. Now, what does this all have to do with today's lesson? We'll see in the next video. Lesson 18 on binomial distributions. So it turns out that the Monty Hall problem that we talked about is deeply involved with these binomial distributions. Let's take a look here. So let's say that x, this random variable, represents the number of wins among the 18 rounds played under the switching strategy. Then x has as its distribution a binomial distribution, BIN, where the number of rounds or trials is 18, and the success probability per trial, P, is 2/3. 2/3 is the probability that you win the car under the switching strategy for any given round. Okay, so this is a distribution, all right? So x is a random variable that can take on a value between 0 and 18. If you play 18 rounds of this game, then you can win the car between 0 times and 18 times. X can take on various values between 0 and 18. Now, the binomial distribution involves these possible values of x and their corresponding probabilities. Now, there's almost no chance that you win the car no times or 1 time or 2 times, for example. The most likely number of wins is, look at this, 12 out of 18. That's one reason why I chose 18 rounds. 2/3 of 18 is 12. It turns out that this is the mean for this distribution. Now, the probability that you win the car 12 times out of 18 under the switching strategy is about 20%, 0.196, and is the highest probability of all of these. So it's not surprising that 12 is the most likely number because 2/3 is the success probability. 12 is 2/3 of 18. So this is the probability distribution for x, the number of wins out of 18 rounds. It's almost 0 over here. Then it goes up, 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 and it peaks at 12 wins out of 18 rounds, then down, 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 and it's very unlikely that you win the car all the time. Of course, these probabilities add up to 1, give or take rounding error. Now, actually, we saw this in practice, at least I did. In 5 of my statistics classes, 101 pairs or teams of students played this Monty Hall game. They played 18 rounds of this game, and they recorded the number of times that the student contestant won the car out of the 18 times. For each pair, the contestant was one student and Monty Hall was the other student.
Money Hall.
So, based on the 101 teams, no team saw these numbers of wins for the car, 6 or fewer. Nobody saw 6 or fewer wins in this switching strategy. But as a matter of relative frequency, it went up, 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 up. This time it peaked at 11, but 12 was also pretty high over here. But you saw the highest relative frequencies for basically 11, 12, 13 wins out of 18. Now, as you see, the relative frequencies that I actually observed in my 5 classes, they did not match the theoretical probabilities perfectly, but they were pretty close. They were pretty close. And again, we saw a peak at around 2/3 of the 18 rounds, about 12 or 13. Okay, so we're seeing the binomial probabilities playing out in these relative frequencies, and I can guarantee you that if instead of 101 teams, if I had 1,000 teams or 10,000 teams, then the relative frequencies would have very closely matched the theoretical probabilities over here. Okay, so this is an example of a binomial distribution. What defines a binomial distribution? All right, what is a binomial experiment? First of all, okay, so basically the Monty Hall game that we played and this game we're going to talk about here, they're going to represent binomial experiments, which give rise to binomial distributions. So let's say that I'm playing Yahtzee and I roll a standard 6-sided die 5 times, or equivalently, I roll 5 such dice at the same time. Let's say that we count the number of 4s on the 6 dice.
5 dice.
Let X be the number of rolls or the number of dice coming up of 4 among the 6 faces. Now this is a binomial experiment, and X, which counts the number of 4s, is a binomial random variable. Now why is this a binomial experiment? Okay, so first of all, and don't worry, you won't be tested on this, but you need to know a binomial experiment when you see it. First of all, we see a fixed number of independent trials. In this case, for the dice, 5 rolls or 5 dice. For Monty Hall, it was 18 rounds for each of the student teams. Each trial results in either a success or a failure. So with the Monty Hall rounds, the contestant either won the car or didn't. For the dice, a success is when a 4 is rolled. A failure is when something else is rolled, like a 5 or a 6, or a 1, 2, or 3. So the idea is that we're counting successes. X is a binomial random variable that counts successes, which would be car wins in Monty Hall or 4s in this dice example over here. In some medical situations, X could count deaths, in which case you may not want to be successful. Number 3, for each trial, there is a fixed probability of success. And we call that fixed probability P. In the case of dice, P, the probability of rolling a 4, is 1/6. The failure probability is the complement. It's 1 minus P, or what we call Q, the failure probability. Q is 1 minus 1/6, or 5/6. It's the probability that a die comes up something other than a 4. In the Monty Hall problem, P is 2/3 and Q is 1/3. Okay, so in both the dice example here and the Monty Hall problem, we're talking about binomial random variables, X, which counts the number of successes from a binomial experiment. Another classic situation is when you're flipping coins. Here is another Rossmann chance applet. Let's say that we take a fair coin, probability of heads is 0.5, and we toss the coin, how about 100 times, like many of you did in the extra credit problem. Okay, let's draw the samples, all right? And this particular student got heads 44 times and tails 56 times. Okay, now let's say that instead of 1 student, we had 1,000 students flipping 100 coins. So 1,000 students doing this extra credit problem. Let's draw the samples, all right? This was the last student. We care really about this relative frequency histogram over here. You can see that it's peaking at about 50 heads out of 100. Now, this is what we're seeing from the simulation.
And by the way, that's a straight up frequency histogram. These are straight counts here, not relative frequency.
Where 1,000 students are flipping a coin 100 times, a fair coin 100 times. According to the binomial distribution, the frequency distribution should look something like this in green. And as you can see, it very closely models what we actually saw from our simulation. And guess what? This binomial histogram very much resembles a normal bell curve. And in fact, we're going to investigate that later on. The fact that normal bell curves can sometimes approximate binomial histograms. Okay, so we're going to talk more about binomial experiments and binomial distributions in our next video.
All right, before we do that, I'd like you to play with this applet. Again, I sent you the link. And if you didn't get the link, I'll show you what you do again. So you can go to rossmanchance.com. I already have it in here. rossmanchance.com. All right. Rossman Chance applet collection. All right. Again, it's in the upper right. It's under, okay. It's the first one under statistical inference, one proportion inference. Okay. I know it's not a very good name for it, but it's under one proportion inference. Click on that. All right. Now here we have fair coins, right? The probability of heads is 0.5. Although you can change that. You can make it anywhere from 0 to 1, right? Number of tosses. Let's say we toss it 100 times, like you did for the extra credit. Some of you, all right? Well, if we do that, right? Draw samples, right? Okay, this person gets 49 heads and 51 tails. There's a little dot on the dot plot there, right? Let's reset it. Let's say 1,000 students. Let's say we have 1,000 students in a big lecture hall class. They each flip a coin 100 times. Let's look at their relative frequency or their frequency histogram. Hey, folks, you do this. Okay, have 1,000 students. Have the computer, this applet, have 1,000 students each flip the coin, the fair coin, 100 times. See what kind of histogram you get. Do you all get pretty much a normal bell shape, pretty much? If anything, this looks kind of bimodal almost, actually. But what do you see? Yeah, it should pretty much be a bell shape. Again, I'm kind of surprised how kind of bimodal this kind of looks, but yeah, bell shape. Although, if one of you doesn't get it, that could be due to sampling error, all right? Right, and remember, this thing here is what the 1,000 student gets, right? And the idea is that you have 1,000 students getting like 50 heads or whatever, right? Okay, good. All right, so again, I emailed that link to you folks, all right? We're still recording, right? Gotta check. Yep, okay. I never stopped.
Hi, everyone. We're continuing with Lesson 18 on binomial distributions. So far, we've talked about 3 binomial experiments that give rise to 3 different binomial distributions. These are distributions for X, a binomial random variable, which counts successes. So in the Monty Hall problem, we had students in teams play 18 rounds of the Monty Hall game. X counted the number of successes among those 18 rounds. And it turned out that X had a binomial distribution where N, the number of trials or rounds, was 18, and P, the success probability per round, was, perhaps surprisingly, 2/3, not 1/2. And we saw that this distribution in tabular form looked like this. X, the number of wins, went from 0 to 18, and here are the corresponding probabilities with a peak at 12. Now, this is a binomial distribution because we have a fixed number of independent trials, n equals 18, and what happens in one round does not impact another round. Each trial results in a success or a failure. A success means, of course, you win the car. A failure means you win the goat. And the success probability is fixed. It's 2/3, and it does not change from trial to trial, from round to round. Now, I also mentioned a coin experiment. Let's look at the Rossman Chance applet. Let's say we have a fair coin. where the probability of heads is 0.5. And let's say that a success is heads, not tails. Although remember, something like a death could be a success. Here, a success is heads. Let's say that the coin is flipped 100 times. Okay, so this student gets 54 heads and 46 tails. You see the little dot there on the 54. It's a dot plot. You see the dot there for 54. Okay, now let's say that we repeat this 1,000 more times. 1,000 more students flip the coin 100 times. So for the 1,001 students, this is the frequency histogram for the number of heads. The binomial histogram, where n equals 100, I'll bring this up here, where n equals 100, and p equals 1/2 or 0.5. The binomial distribution where n is 100 and p is 1/2 or 0.5. The histogram is in green over here, and it closely matches what we see from the frequency histogram. Okay, so again, in this coin experiment, we're seeing a binomial distribution for x, the number of heads. And this is, in green, a frequency distribution for x. Okay, so why do we have a binomial experiment in the coin situation? Because again, we have a fixed number of independent trials, n equals 100. Each trial results in a success or a failure. A success means a head, a failure means a tail. And for each trial, there is a fixed probability of success. For a fair coin, p equals 1/2, and that does not change. The coin is not made of bread. P stays at 1/2. It's made of solid metal. Okay, p is 1/2, q is 1/2. So in the coin situation, if x is the number of heads, the number of successes, then x has, as its distribution, a binomial distribution where n, the number of trials, is 100, and p, the success probability per trial, is 1/2 or 0.5, the probability of heads. Now, in the dice situation, this is where we're rolling a die 5 times, or we're rolling 5 dice, and x is counting the number of 4s that we get. Well, n equals 5 is the number of dice that we roll. A success means you get a 4, a failure means you don't. We have a fixed probability of success. It's 1/6. That's the probability of getting a 4. The probability of not getting a 4 is 5/6. So in our dice example, if x is the number of successes, the number of 4s among the 5 trials or dice, then x has a binomial probability distribution. X is binomially distributed where n is 5 and p is 1/6. N and p are the parameters for this distribution. If you change one of them, you change the distribution. If you change the number of dice, if you change the probability of a 4, then that changes the distribution. It turns out that the distribution table for this binomial distribution is this. Of course, we can get between 0 and 5 4s among the 5 dice. The probability of getting no 4s is about 40%. Coincidentally, the probability of getting 1 4 among the 5 dice is the same, about 40%. The probability of getting all 4s on the 5 dice is almost 0. It's not quite 0, so we put 0 plus, because it's very powerful to say that something's impossible. It's not impossible to get 5 4s on the 5 dice, but it's pretty close to 0. It's 0 to 3 decimal places. In fact, the probability of getting 5 4s on the 5 dice is about 0.000129. It's very close to 0. Okay, now, again, this is a dice scenario where we're counting the number of 4s among 5 dice, or among 5 die rolls. But there are other binomial experiments that give rise to this distribution. Going up the notes here, similar examples. Let's say that 1/6 of all Americans have cooties, this disease. We randomly sample 5 Americans. Now, I know that technically we have dependence here. but by the sampling rule, we can assume independence. The probability we get the same person twice by chance is minute. Let X be the number of Americans in the sample with cooties. So we have a binomial experiment here because we have independence. We have 5 trials, the 5 Americans. Each trial ends up in a success or a failure. Here, a success means you have cooties, so you may not want to be successful. And the success probability, 1/6, is the same for all 5 Americans. Again, we're assuming independence under the sampling rule. Let X be the number of Americans in the sample with cooties, and lo and behold, it's the same distribution. It's a binomial distribution where N, the number of trials, is 5, and the success probability, the probability that a given person, American, has cooties, is 1/6. And the binomial distribution looks like this. There's about a 40% chance that nobody among the 5 Americans has cooties, about a 40% chance that 1 American among the 5 has cooties, and so on. Another experiment that gives rise to the same distribution, a multiple choice test has 5 questions, so N equals 5. Each with options A through F. That's 6 possible options. A student guesses randomly on all 5 questions. So the success probability per question is 1/6. On any given question, there are 6 possible options, A through F. The student guesses randomly. There's a 1 in 6 chance that the student gets the question correct. Let X be the number of correct answers or responses. So on a test with 5 questions, X could be between 0 and 5. Okay, X counts the number of successes, and again, it has the same binomial distribution we've discussed. N equals 5 trials or questions, P equals 1/6, the shared probability of success. In this case, the student guesses randomly. On any given question, 6 options, P is 1/6. So in all 3 of these cases, actually, now it's 5 examples where we have a binomial experiment. I just described 3 experiments where we have the same binomial distribution. We roll 5 dice and we count the number of 4s. X, the number of 4s we get, has a binomial distribution, N equals 5, P equals 1/6. In the cooties example, N equals 5 Americans, that's the number of people in our sample, the sample size. 1/6, that's the probability that any given American has cooties. On this multiple choice test, N equals 5 questions, P equals 1/6, because each question has 6 options and the student guesses randomly. So for the student, the probability the student gets no questions correct, all wrong, is about 40%. The probability the student gets exactly 1 question correct turns out to be the same, about 40%. And there's almost no chance that the student gets all 5 questions correct. It's this over here. Okay, so we'll continue with this in the next lesson.
It's funny. When we were on campus, students would often tell me, "Hey, Ken, we wish we could pause and rewind you." So now they can. All right. Any questions, by the way? Any questions? Examples of binomial probability distributions and some settings, right? Any questions? All right. So going on. All right, going on. Still mad.
Hi everyone, we're continuing with lesson 18 on binomial distributions. And last time we really focused on this one particular distribution, this binomial distribution where N equals 5 trials and success probability P equals 1/6. This is the distribution in tabular form. And we saw applications of this to rolling dice and counting the number of 4s, to the cooties example, where we took 5 random Americans and counted the number of cooties cases, and the multiple choice test with 5 questions, each A through F. The student guesses randomly, and we count the number of questions the student gets correct. Actually, we can modify the coin situation for this distribution. Now, in the usual situation, we have students flip a fair coin 100 times. A head is a success, and X counts the number of heads or successes. Then X has a binomial distribution where N equals 100 flips or tosses, and success probability head probability, P, is 1/2 or 0.5. So let's say that P is 0.5, the probability of heads. We have N equals 100 flips or tosses. This student gets 51 heads and 49 tails. We see a dot at 51 on the dot plot. Let's say that 1,000 more students join in the fun, do the same thing. Student number 1001 gets 52 heads over here. And here is a frequency histogram for the number of heads, the value of X, obtained by the 1001 students. Now, what would the corresponding binomial probability distribution predict in terms of the frequency histogram? It predicts what's in green, which is a pretty close model for what we actually see in our simulation. Now, this green histogram is given to us by this distribution, a binomial distribution where N equals 100 and P equals 0.5. That's the ideal theoretical distribution in green. Now, what happens if we consider this alternate distribution where N equals 5? We're just rolling 5 dice or flipping 5 coins here. But this time, the probability of success P is 1/6. So we're modeling rolling 5 dice where we're counting the number of 4s, or we're flipping a very unfair and biased coin where the probability of heads is 1/6, not 1/2. So let's say the probability of heads is about 1/6, about 0.167. That's the decimal equivalent rounded off. Okay. 5 flips or 5 rolls of a die. One sample. Let's see what happens with one student. Now here it looks a bit different. So basically, it's like a student rolling the die 5 times, or rolling 5 dice, or flipping a biased coin 5 times. So each of these wheels here corresponds to a die roll or coin flip. Now, 1/6 is the proportion of each disc that's blue. That corresponds to a success. So if the spinner lands in the blue wedge, that counts as a success. For example, here, this barely counts as a success. The spinner barely enters that blue wedge, that counts as a success, which means that the die came up a 4 or the biased coin came up heads. But in these 4 other rolls or flips, the spinner landed in the pink area, which corresponds to a failure, or 5/6 of the pie. So we had 4 failures over here because the spinner landed in the pink failure pieces of the pie. So among these 5 die rolls or coin flips, we had 1 success, just barely, and 4 failures, 1 head and 4 tails, if 1/6 is the probability of heads. Now what happens if we do this? Let's turn off the binomial. Let's say that we do this 1,000 more times. Notice that the dot here indicates we had 1 success for this one student rolling 5 dice. If we have
By the way, there's a little dot there at the 1 because you didn't see it.
1,000 more students, here was the result for student number 1001. Again, 1 success. Okay, so it looks like we have a bunch.
So yeah, it's covering it up. But yeah, you can see that, remember the probably about 40% for none, no successes, about 40% for 1 success, about 16%, so on, right?
Of students who got either no 4s or 1 4, fewer students with 2 4s, even fewer students with 3 4s. Or in the context of coins, remember, it's a very biased coin where the probability of heads is 1/6. We had many students who got no heads, many students who got exactly 1 head, fewer students who got 2 heads out of the 5 flips, fewer. Okay. By the way, what does the binomial distribution over here predict? The binomial distribution predicts this frequency histogram over here in green. So again, the binomial histogram, or really the frequency histogram predicted by the binomial distribution does a very good job of the actual frequency distribution we see for the 1,001 students.
All right, so to show what it is, right? So the actual observed frequencies you see in the black bars, and you'll see that the frequencies predicted by the theoretical probabilities under the binomial distribution, that's in green. You see they're very close, right? The green and the black bars are very close. So the green bars did a very good job of modeling and predicting what we were going to get.
Okay, so here again, we're looking at a twisted or biased coin situation where we end up with the same binomial distribution as this guy over here. What we see is what we get. I mean, in terms of the actual simulation, we get a frequency histogram that's very close to what the exact binomial distribution predicts for us. All right. So now, back to these notes. Now, fortunately, the notes that are primarily handwritten, these will not be on the homework or the exam. This describes how the probabilities are computed. I'll discuss these in later optional videos. Now, what's still required? Well, first of all, we have the sampling rule. Remember, when we had the Cooties example, we were drawing a random sample of 5 random American adults, I guess, from the overall population. And by the sampling rule, we could still assume independence. We could still have a binomial experiment because the sample size, little n, was tiny. It was only 5. And it was certainly no more than 5% of the overall population size of American adults, which is in the millions. Okay, so we could assume independence. That's a side note. What else would be fair game for homework or potential exams? Well, let's say that we have this example here. Example 2.
Yeah, don't worry, we're not having exams, but I want to keep my options open.
Using tables to analyze binomial distributions. Let's say that 70% of American adults like Senator Smith. That is, the probability that a random American adult like Senator Smith is 0.7. Bear in mind, there's often a direct relationship between proportions and probabilities. 70% of American adults like Senator Smith, that's a proportion. That's readily translated as a probability. The probability that a random American adult like Senator Smith is 70% or 0.7. There's often a relationship between proportions and probabilities. Now let's say that 6 American adults are randomly sampled to form a focus group, and we want to ask them questions about Senator Smith, their opinions of Senator Smith. Find the probability that at least 4 of the people in this focus group of 6 like Senator Smith. Big hint, we have this table here. Now, on an exam, it's fair game for you to be required to know that the distribution we're talking about is this distribution. If we let X be the number of people in the focus group who like Senator Smith, then X has this as the distribution, a binomial distribution where n equals 6, that's the number of trials, the sample size, the number of people in the focus group, and p equals 0.7, the success probability per American adult.
Watch out, captions.
Now, we're saying here that a success means that an American adult likes Senator Smith, and we're counting successes. So X, the number of successes, can be an integer between 0 and 6. And it turns out that these are the corresponding binomial probabilities. Now, on an exam or a homework problem, I would give you this table of probabilities. Later on, in optional sections of videos, I will discuss how these probabilities are actually obtained. But for homework and or exams, I would actually give you this probability table, this probability distribution table. It's a table for this distribution. Okay, so the probability that nobody in the group likes Smith is almost 0. Bear in mind, Senator Smith is pretty popular, and the probability that nobody among the 6 people in the group like Smith is almost nothing. Now, 70% of American adults like Smith. It's not surprising that the most likely number of people in the group who like Smith is 4. 4 out of 6 is pretty close to 70%. 2/3 is pretty close to 70%. The probability that exactly 4 people like Smith is 0.324. After that, the probabilities go down. The probability that all 6 people like Smith, it's lower, 0.118, but not terribly low. Senator Smith is very popular, and the probability that all 6 like Smith, it's not too low. It's lower than the probability of 4 liking Smith, but it's not that close to 0 either. Okay, so given this probability distribution table, my question here was, find the probability that at least 4 people in the focus group like Senator Smith. So this is similar to what we've done before. What's the probability that X is at least 4? Basically, we're focusing on these 3 rows of the table, and we want to add these probabilities. Remember, at least 4 includes 4, so we want to include this probability, and we also want to go higher. We also want P of 5 and P of 6. In the end, we want to add P of 4, the probability of exactly 4 people liking Smith, P of 5, the probability of exactly 5 people liking Smith, and P of 6, the probability that all 6 people like Smith. We're going to add these probabilities. Again, these probabilities are fairly high because Senator Smith is popular. The probability that X is at least 4 is P of 4 plus P of 5 plus P of 6. We add up these 3 probabilities, we get 0.745. So about a 3 in 4 chance that at least 4 people in the group of 6 like Senator Smith. And that would be fair for a homework or exam question. So afterwards, we're going to deal with basically optional videos where I'll discuss how these probabilities are computed. But we're going to talk game shows, and we're going to have fun as well. I'll see you later.
Okay, to be honest, that's what you need for the homework, okay? But I want to explain the binomial formula and why it works. And there's some real beauty here. It's some of my favorite parts of math. And we're going to start with one of my favorite game shows of all time, The Price is Right. And, well, you'll see it. You'll see my favorite game in Price is Right. It was a lot of people's favorite game. And on this one, let me see here. Yeah, actually, I can play this one. I can play The Price is Right. No one cares. All right, we can do this. I can cut it out if there's a problem.
Christy today.
Rich, what do we have for Christy today?
Christy, you're going to play Plinko for a chance to win up to $50,000.
Scott, come over here, Christy. Wait a minute. And the last item, please.
Finally, this clever trio of solid wood nutcrackers dressed as court jesters is a fun addition to your Christmas decor.
3 of them. Starts with the 5, goes to the 1.
Begins with 5.
Starts with a 5. She says, yes! 5 Plinko chips. Thanks, Rachel. Here comes Tamiko with your Plinko chips. Right over here. And up the stairs you go. Up those stairs you go with all your Plinko chips, Christy. Thanks, Tamiko. Now, you know what you got to do. One at a time, you're going to put them flat against the wall, let it drop. You want $10,000 right in the middle here. That's what you want to get 5 times. Just put it up flat against the wall and drop it whenever you're ready. There you go. Come on down. Come on down to 10,000, 10,000, 10,000, 10,000, 10,000, 10,000. Oh! So close. Right there. That's where you want it. That was really close. Really close. Really close. There we go. Right down the side. Back in the middle. Back in the middle. There you go. Stay in the middle. Stay in the middle. 10,000, 10,000, 10,000. Do it one more time. Right there. That's where you want it. She's trying to figure out where she put it the last time. It's like bowling, isn't it? You just got to figure out where you put it the last time, and it'll all be okay. 10,000. $20,000. $20,000 so far. One more time. Don't lose your mojo, Christy. I don't know. I can't remember. Somewhere right around there. $20,000. 20,000. Here it comes. Back in the middle. Back in the middle. Oh no. $100. 20,000. 100. This could be a record breaker. You get that extra $10,000. You got one left. What's the record? The record's 23,000. You get that 10,000, you're going to set a record for Plinko. If you get the 10,000 again, you're going to set a record for the most won on Plinko. Here it comes. Oh, bounce left. Stay in the middle. Stay in the middle. Come on down. Get in the middle. A new Plinko record. A new Plinko record. 30,000. Come on down here. A new Plinko record. 36 years of Price is Right. $30,000 for Christy. That's the most anybody's ever won for a Plinko. We'll be right back with more Price is Right after this.
All right. So what does this have to do with what we're doing?
Hi, everyone. We're continuing with lesson 18 on binomial distributions. This was the problem that we did last time. Later on in part F, these are handwritten notes, and these are notes that we'll cover much later on. They're optional for now. So I'm going to go over the handwritten optional notes backwards. So again, part F, we're not going to deal with right now. Part C, you won't have to know for the exam, but it's one of the most beautiful things in math. So let's go to more beautiful websites. Pascal's triangle, which is really optional. And folks, believe it or not, this here is Pascal's triangle.
So this
One
is
of the favorite games on The Price is Right.
so this is where I play the Plinko
Let's
thing.
go down to ask Rich what we have for Christy today.
All right.
Rich, what
But we're
We'll be right back with more Price is Right after this.
see it's chocolates
So
on YouTube.
That is the Pascal's triangle. Plinko is Pascal's triangle. Let's go to this great website, mathisfun.com, which does a great job with Pascal's triangle.
I'll send the
So
link out.
how is Pascal's triangle constructed? You might remember this from your algebra class. So
What's
you start
that?
off with a tent of ones. So you have ones along this edge and ones along this edge, like a pyramid. Now, every time you have two consecutive numbers, they give birth to their son, their sum. So, for example, here, the 1 and the 3 give birth to a 4. So up here, 1 and 1 give 2. Over here, 1 and 2 give 3. 2 and 1 give 3. And then here, 1 and 3 give 4, as they show. 3 and 3 give 6. 3 and 1 give 4. By the way, one of the properties of Pascal's triangle is that it is symmetric. If you draw an axis here, you see the left and the right mirror each other. The left half and the right half mirror each other. And Pascal's triangle is gorgeous. There are so many patterns. Of course, you have ones along this diagonal. You have the positive integers on this diagonal, the triangular numbers. Imagine dots like 1, 2, 3, right? On this diagonal. Again, we have symmetry, left side and right side. If you add up the sums, and we'll see why this is true, 1, 2, 4, 8, 16, and so forth, powers of 2. And there are reasons for that. Surprisingly, exponents of 11 are hidden in here, powers of 11. The Fibonacci sequence, remember, 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5. Each successive Fibonacci number is the sum of the two prior Fibonacci numbers. It's a famous sequence, and it's also hiding in Pascal's triangle. If you shade in all the odd entries, and you do it for many rows, you get the Sierpinski triangle or gasket. It's this thing, which is a famous creature in chaos and fractal theory. The idea that basic rules lead to these elaborate, complex patterns. Okay, now we saw the powers of 2 before, and this kind of explains why. For example, consider 3 flips or tosses of a coin, fair or not, right? Well, how many possible sequences of 3 heads or tails can we have? Well, we have 3 flips or 3 positions. Each position can be a head or a tail, right? So we have 2 possibilities for the first flip, 2 possibilities for the second, and 2 possibilities for the third. 2 times 2 times 2 is 8. Now, Pascal's triangle, let's look at this. 3 flips or tosses of a coin, fair or not, all right? Notice there's only one way to get 0 tails and 3 heads, 3 ways to get 1 tail and 2 heads, 3 ways to get 2 tails and 1 head, and only 1 way to get all 3 tails. These are the numbers in Pascal's triangle on row number 3. Bear in mind, when you look at Pascal's triangle, row number 0 is on top. So row number 0 has the 1. Here's row number 1, row number 2, row number 3, and so forth. You can look at the second number in the row to see what row number we're talking about. Now, it turns out that Pascal's triangle is this list of binomial coefficients over here. N choose K, or NCR. Do you remember those numbers? Remember 52 choose 5, or 52 C5, the number of possible poker hands from a deck of 52 cards? That's 52 choose 5. That's way down in the table in Pascal's triangle, but it's there. So basically, if you're like Vanna White on another game show, if you flip these binomial coefficients around, these NCR values, you're going to get Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and so forth. Here are the first 15 lines of Pascal's triangle, rows 0 to 14, and the ancient Chinese knew about it. I want to go back to why it is that these binomial coefficients, these NCR numbers, the number of combinations of n items taken R at a time, like poker hands, why they correspond to Pascal's triangle. All right. Well, again, this is why it's Plinko. Let's go back to this Plinko board over here, this Pascal's triangle. All right. In fact, I'll go to the very top. All right. So how many ways are there to hit this pin over here? Imagine that each of these squares corresponds to a pin. How many ways are there to hit this pin over here? 3 choose 1 or 3. Left, left, right, left, right, left, and right, left, left. We're imagining these falling chips. How many ways are there to hit this pin over here? Only one way. Left, left, left. Well, there's one way to hit this pin and 3 ways to hit this pin. How many ways are there to hit this pin? 1 through here, and then go right, 3 through here, and then go left, 4 ways to hit this pin. So the number on each of these squares, these numbers in Pascal's triangle, they correspond to the number of ways that the chip can hit that pin. Let's go back here. Why is this 3 choose 1? 3 choose 1 is 3, all right? So 3 drops, n equals 3. A right is a success. Right is a success. So left, failure, right, success. That's one way to get 1 success and 2 failures. Left, failure, right, success, left, failure. Again, another way to get 1 success and 2 failures. 1 right, 1 success, 1 left, a failure, another left, a failure. So how many ways are there to get 1 success and 2 failures out of 3 trials or 3 drops? 3 ways, 3 choose 1. So that's an example of why Pascal's triangle is a table of these binomial coefficients, the number of combinations, NCR, n items taken R at a time. Again, 52 choose 5 is way down here, about 2.6 million. At the very bottom, again, the Plinko board. It's called a quincunx. So let's say that it's 50-50. P is 0.5 in a binomial distribution. Let's speed it up. Here, n equals 6, p equals 0.5. And we're looking at what a binomial distribution, where n equals 6 and p equals 1/2, what that histogram would look like. Take a look at this. It's looking more and more bell-shaped. What if we up it to 15? N equals, let's restart this. N equals 15, p equals 0.5. Sped up, looking down there. N equals 15, p equals 0.5. Binomial distribution. Again, a right is a success, a left is a failure. Each drop is a trial, which means that these numbers here correspond to the number of successes. If you're a student who gets all 15 questions correct on a true-false exam, for example, then you'd be in this bin over here. Not very likely, though. And again, it looks more and more bell-shaped.
Just have you look at what this looks like. It looks kind of bell-shaped. Yeah, you see this in science museums.
All right. And they explain the quincunx over here. Again, it's a great website. Great website. Okay, and a normal distribution approximates that. But Pascal's triangle is absolutely gorgeous and is relevant to the binomial distribution, as we'll see in the next video.
Again, this is optional, but I want to explain why the binomial probability formula works. So it gets to a point here.
Hey everyone, we're finishing up lesson 18 on binomial distributions.
We'll have a couple more videos.
But we took a detour towards Pascal's triangle, which is one of the most beautiful things in math. I talked mostly about it last time, but I wanted to add in a few finishing touches here. This is a handout I created about the magic of Pascal's triangle. So as a quick reminder, remember we put ones along these edges of this tent or pyramid here, right? And every time we get two consecutive numbers, they give birth to their sum. Their sum is a sum. So 1 + 1 is 2, 1 + 2 is 3, 2 + 1 is 3, and so forth. And I claimed that these numbers in Pascal's triangle were in fact these binomial coefficients, these numbers of combinations, n choose r. So for example, 3 choose 1 is 3. And that corresponds to the number of ways for a Plinko chip to hit the 3. There are 3 drops, n equals 3, drop, drop, drop. Okay, a right is a success, a left is a failure. So how many ways can you get one success out of 3 trials? One right out of 3 drops? Well, left, left, right, left, right, left, and right, left, left. 3 choose 1 is 3. Now, how is this related to the binomial theorem from algebra? So you might remember from algebra class that a plus b all to the third can be written like this, right? Where for the variable parts, we start with a to the third, we decrease the exponent by 1 until the a disappears, and then for b starts off as b to the 0, which is 1, which is invisible, and then we get b to the second, b to the third. And the coefficients for this power of a binomial, right? These coefficients come from Pascal's triangle. It's these binomial coefficients, these n choose x guys. N choose 0, n choose 1, n choose 2, n choose 3. 3 choose 0 is 1, 3 choose 1 is 3, 3 choose 2 is 3, 3 choose 3 is 1. Now, why does that make sense? How do we get the cube of a plus b? Well, if you cube anything, you take 3 copies of that thing, here, a plus b, and you multiply them together. And you can distribute like crazy. But basically, when you perform the distribution, for each term, you get a choice from here, a choice from here, and a choice from here. It's kind of like if you have 3 meals in a day: breakfast, lunch, and dinner. For breakfast, you can pick super salad, A or B. For lunch, A or B, super salad. For dinner, A or B, super salad. Okay, now, again, instead of...
Oh my gosh, I just realized in these days of the virus, that's not so unrealistic, is it?
salad, we can talk about B, or a success, or getting a question right, or getting ahead, okay? So basically, if you choose a term from here, and then choose a term from here, and then choose a term from here, there are 8 ways to do that. 2 times 2 times 2. 2 to the third is 8. So you could have all soup, right? A. That could be all failures. The number of ways to get 0 successes out of 3 trials. The number of ways to get 0 questions correct on a 3-question exam, 1 way. Wrong, wrong, wrong. A is wrong, B is right. But how many ways can you get 1 question right and 2 questions wrong? How many ways can you get 1 success out of 3 trials? Well, you could have wrong, wrong, right, wrong, and right, wrong, wrong. When you add these together, you get 3 A squared B. The 3 here is the number of ways to get 1 question right out of 3 questions. Likewise, 3 choose 2 is also 3. That's from symmetry. the number of ways to get one question right out of 3 is equal to the number of ways of getting one question wrong out of 3, or 2 questions right out of 3. So there are 3 ways to do that. You add these up, and you get 3ab squared. These 3 guys here. And then there's only one way to get all 3 questions correct on a 3-question exam. Correct, correct, correct. That's b cubed. Add these all together, and you get the expansion of the cube of a plus b. So if you love algebra, I'm sure you love that. Okay.
Basically, if you take a 3-question exam, okay, then your result has to be one of these, right? Like, for example, here, it's like wrong, right, right. Okay? On a 3-question exam, you get each question either right or wrong. Here are the 8 possibilities.
So if you love algebra, I'm sure you love that. Okay, so how do we use these ideas to figure out binomial probabilities? It's all related. The binomial theorem, right? These binomial coefficients, and binomial distributions with their binomial probabilities. So for example, if you have a student taking a multiple choice test with 5 questions, n equals 5 trials or questions, and each question is A through F, 6 options, and the student guesses randomly on each question. The student knows nothing about the material and guesses randomly. So the probability of getting any given question correct is 1 out of 6. Let X be the number of successes, the number of questions the student answers correctly from guessing randomly on this test. The possible values are 0 through 5. The student could get all the questions wrong, 1 question correct, 2 correct, 3 correct, 4 correct, or all 5 correct. And here are the corresponding probabilities. But how can we figure out these probabilities? Again, this is optional for the homework and the exam, but it's good to see. All right, well, you could have software or TI graphic calculators. You could have printed tables, or the old school way of doing it, the binomial probability formula. The probability of X successes equals N choose X, or NCX. That's a binomial coefficient. Like 52 choose 5 was the number of 5-card hands you can get from a deck of 52 cards. N choose X, or NCX, is the number of ways that a student can get X questions correct out of N questions. So for example, how can a student get, let's see.
I think I made an error. That's why I had to kind of break in there.
3 questions correct out of 5. 3 questions correct out of 5. 3 questions correct out of 5. It turns out there are 10 ways. 5C3, or 5 choose 3, is equal to 10. For example, the student could get question 1 correct, question 2 correct, and question 3 correct. The student could get question 1 correct, question 2 correct, and question 4 correct. The student could get the last 3 questions correct, number 3, number 4, and number 5. It turns out there are 5 choose 3, or 10 ways of doing this. All right, so N choose X is the number of ways that a student can get X questions right out of N questions. P is the success probability per question. X is the number of successes. Q is the failure probability per question. And minus X is the number of failures. So for example, if there are 5 questions, if N equals 5 questions, X equals 3 correct, then N minus X equals 2 wrong or incorrect. Okay, so you can make these computations. Probability of 0 correct. That's the probability of getting all 5 wrong. It makes sense that it's 5/6 to the 5th. The probability of getting each question wrong is 5/6. Multiply 5 copies of this by independence, and you get about 40%, 0.402. Remember, on your calculator, make sure you process 5 divided by 6 first before raising to the 5th power. P of 1, 5 ways to get 1 question correct out of 5, and only 1 question correct, right? Again, about 40%. That's a coincidence. The probability of 2 questions correct, that's about 16%. The probability of 3 questions correct, the probability of 3 questions correct. Let's go through this in detail. 5 choose 3, 5 see 3. We just mentioned that that binomial coefficient was 10. There are 10 ways of getting 3 questions correct and 2 questions wrong on a test of 5 questions. That's 10. All right, the probability of getting each question correct is 1/6 because it was A through F for each question. 6 possible options. The student is guessing randomly. 3 questions correct, 1/6 to the third. The probability of failure, the probability of getting a question wrong, Q, is 5/6, which is 1 minus a sixth. 5/6 to the number of failures or questions wrong, that's 2. Put these all together, 0.032, or about a 3% chance that the student gets exactly 3 questions correct out of 5 based on random guessing. P of 4 is smaller. P of 5 is very, very tiny because you have, for example, 1/6 to the fifth over here, which is teeny tiny. 5/6 to the 0 is 1. 5 choose 5 is 1. So it's basically 1/6 to the fifth. The probability of getting 5 questions correct, success probability of 1/6 for each question, 1/6 times 1/6 times 1/6 times 1/6 times 1/6, it's almost 0. It's this. So that's how you calculate the probabilities.
By the way, if you ever forget to close caption, remember in the when I post these on YouTube, the full class session, it captions, and also I have the originals; they're captioned.
Okay. So when all is said and done, you end up with this binomial formula. Applying it, you get this. For this distribution, here is the probability table. The binomial probability distribution for this distribution as a table. Now, why does this make sense? Why does this make sense? Okay, so let's take a look at one way to get 3 questions correct out of 5. Well, one way to get 3 questions correct out of 5 is you get the first correct, the second correct, and the third correct. Whereas number 4 and number 5 are wrong. So what's the probability of getting number 1 correct by random guessing? 1 out of 6, which is the value of P. The probability of getting number 2 correct, 1/6. The probability of getting number 3 correct, 1/6. Now the probability of getting number 4 wrong is 5/6, which is Q. And the probability of getting number 5 wrong is 5/6, which is Q. So that's one way to get 3 questions correct out of 5, if you get the first 3 correct and the last 2 wrong. The thing is, though, there are more ways of getting 3 questions correct out of 5 questions. In fact, there are 10 ways, 5 choose 3 or 10 ways, which means that this probability, this is the probability of getting question 1 correct, question 2 correct, question 3 correct, and question 4 wrong, and question 5 wrong. This is only one way of getting 3 questions correct out of 5. And this is the probability of that one particular way. But there are 10 ways to get 3 questions correct out of 5. So this has to be multiplied by the 10. Hence, P of 3 looks like this. 10 ways to get 3 questions correct out of 5. 1/6 to the third, 5/6 to the second. Because we may as well look at this easy case where the 3 questions you get correct are the first 3. But it's the same probability for all 10 ways of getting 3 questions correct out of 5. Again, that's how you get the table. You don't have to know that for homework or exams. And that, my friends, is the binomial distribution.
But I keep going on. There's a bit more, right? Yeah, 3 minutes. Sorry.
Hello again. I wanted to explain.
Yeah, you ever see the last film in the Lord of the Rings trilogy? You never know when it ends. You never know when it ends.
Why these binomial distributions are called binomial distributions, and also show you some lovely pictures. So remember, for a binomial experiment, each trial results in a success or a failure. Each trial is binary, success or failure. Just as a bicycle has 2 wheels, A binomial experiment has a binary result for each trial. Each trial results in either a success or a failure. The coin comes up heads, success, or tails, failure. A student gets a question correct, success, or wrong, failure. The die comes up a 4, success, or doesn't, failure. Also, another reason why it's called a binomial distribution, because as I mentioned earlier, it's involved with expanding the powers of binomial expressions. A plus B is a binomial, a two-term polynomial. The cube of A plus B, it can be worked out in this fashion, and these coefficients are called binomial coefficients, the 1, 3, 3, 1. They're called binomial coefficients. Also, these pictures, a gallery of binomial histograms. I have 50 of them here for various values of n, the number of trials, like for example, the number of questions on the test or the number of coin flips, and p, the success probability per trial. For a fair coin, you're looking at the center column. For p equals 1/4, that could be a multiple choice test, A, B, C, D for each. But anyway, look over here, for example. You flip a fair coin 3 times. N equals 3 trials, P equals 1/2. The probability of no successes, no heads, is 1/8. The probability of 1 head is 3/8. The probability of 2 heads is 3/8. The probability of all 3 flips being heads is 1/8. Notice this is symmetric. A related problem, if a student takes a multiple choice test with just 3 questions, maybe it's a short quiz, 3 questions, each of them true, false. The student guesses randomly on all 3 questions. Then again, here's the probability distribution for X, where X is the number of questions correct on the student's part. Now let's examine these binomial histograms and notice, especially in that center column, as n gets larger and larger, n equals 10, p equals 1/2. This is the simplest binomial histogram that we're going to approximate with a normal bell curve. Something to look forward to.
All right, so that was kind of a wrap up. So that's it with the videos. And again, I have the raw videos on my YouTube channel. And I apologize, I forgot to close caption for part of that. But I was recording all the time. I'm not monetizing, so I was recording all the time. All right, so it's 9:37. Thank you for your perseverance. We'll have a good, I can take a few questions now, but we'll have a good general question session on Wednesday. So make sure you bring your homework. We can discuss the homework. And then I'm going to blast through the answers next Monday. So you want to have a good sense of what you're talking about by next Monday, certainly. All right, so that's all for homework part 2. You should have material to finish through lesson 18. We'll talk more on Wednesday, if not in office hours or email. And then next Monday for the answers. All right, and I'll gotta get started grading, right? Yeah. Any general questions? Any general questions? Okay, I'm still recording. Everyone's okay with me recording? Any questions? Okay, oh, sure, go ahead. Go ahead with the, what number on the homework? Okay. Okay, so if you're leaving, good night, everyone, but I'll go ahead and take some questions here. All right, let's see here. Okay, I'll just grab the homework. All right. All right, here we go. Okay, and I do have my printed copy of the answers. All right. Okay. All right, 18-2. All right. Oh, okay. So Here's my deal with you. I'll discuss A and then use that to think about B and C. So let's do 2A. All right. Okay, so 2A on 18. Okay, so this is the lesson we just did today. So I wanted to give people some time to think about it. But we can start off with 2A here. All right. So right, this is the Smith distribution, right? Okay, we discussed this in class. So we have the binomial distribution where n equals 6, 6 trials. P, the success probability is 0.7. That was the Senator Smith problem, right? Okay. Where we count the number of people in the focus group who like Senator Smith. Okay. Now similarly, so in the same way that we can use this we can use this to describe this distribution over here. All right. Now, in a similar fashion, what distribution would describe the random variable here? All right. So we answer all the questions on a true-false test with 50 questions. We guess randomly on all the questions. Okay. So it's like we may as well be flipping a coin. Head is we pick true. Tails is we pick false. So we know nothing about the material on the test. All right. So the random variable is the number of questions. So the random variable x is the number of questions you get correct. What is its distribution, right? Find the distribution that best describes the following. All right. Now, the symbol we use, whoops. The symbol we use is the tilde there. Okay, x has as its distribution, what kind of distribution? What do you call, yeah, you got it right, yeah. What do you, now what's the name of it? What is the name of the type of distribution? Do you remember? Starts with B. Binomial, yes. Binomial distribution. Okay, which we abbreviate BIN, right? Okay, it's called binomial because bi means two. Each trial ends up in either a success or a failure, right? So each trial ends in two possible outcomes, a success or a failure. That's why you say binomial. Okay, yeah, you're right. Binomial, n equals 50. That's the number of questions. You don't need to put the unit, but technically n is 50 questions. And the success probability per question is 1/2 or 0.5. You're exactly right. Okay, so in parts B and C, you're going to give an answer like this, except you need to figure out what the value for n is and what the value for p is. All right? But these will all be binomial distributions. It's a matter of knowing it when you see it. Right? Any questions about that? Any questions? All right, anybody? Okay, oh, you're very welcome, yes. Any questions? I'll wait a minute. If you want me to wait a couple more minutes, let me know, but I'll wait a minute.
I had a question for homework 13.
Okay, first of all, let me adjust the question in chat. Yes, P is 1%. What's 1% as a decimal? What's 1% as a decimal?
0.5?
So you have the 1, right? Yeah, 0.01, right? Because remember, what you do is when you convert from a percent to a decimal, okay, you drop the percent. The decimal point you then move 2 places to the left. All right. The idea is that you're dividing by 100%. That's one way of looking at it. You're dividing by 100%, and that's going to be your decimal value for P. Right. Okay. Sorry. By voice. What question? 13.2. Is that right? 13.2. I don't want to make you dizzy. All right. 13.2. All right, this one here, right? Okay. So 3 cards are randomly drawn from a standard 52 card deck with replacement. That means that you return cards to the deck. So you have independence. That's a key aspect. You have independence between the draws. Okay, it's like you have a fresh, brand new deck of cards with each draw. What is the probability that all three cards are hearts? So we want the probability of heart, heart, heart. Okay, write your answer as an exact fraction and also round it as a decimal, blah, blah. All right. And yes, I can have you remember how cards work, right? So remember, do you know what the probability is of getting hearts? If you have a standard deck of cards, right? What's the probability that a random card is a heart? That probability is 1 over 4. 1 over 4. Because remember, there are 4 suits in a deck of cards. You have hearts, diamonds, clubs, and spades. And remember, and I think I put it in the YouTube playlist. Remember that magician? He was talking about how a deck of cards is set up. Go ahead and review the video. But there are 4 suits. One of them is hearts. Okay, the probability the first card is a heart is 1/4. Okay, and then by independence, remember we're drawing with replacement. We're not throwing cards out. So it's the same probability for all 3 draws. It's 1/4 to the third, in fact. In fact, for your work, I'm okay with either this or writing 1/4 to the third. But you should write something. Right. Yeah, and as a fraction, I know that's 1 over 64. Okay. Okay, and that sounds about right. Although remember, I want 3 significant figures, so that would be more like 0.016 something. Okay, remember, so that would be to 4 decimal places and 3 significant figures. For 3 significant figures, you actually do want a digit here also. Okay, just a comment about rounding. I hope that rounding won't be a big deal in the class, but just one note. 3 significant figures, that would be 0.016 something. Right. Any questions? Any questions? I'm still recording. If anyone wanted me to stop the recording, let me know. But you're welcome. Yes. I think people are cool with it. People are cool with questions. Any questions? I'll wait another minute. Okay. Questions or wait up? Okay. Okay. Would you like me to do this? 13-3? Okay. Discuss that. Do you divide? 3 cards without replacement. Oh, okay. Now here, this is more of a countdown. Okay. So we're going to use the fact that the probability of a heart on the first one, you might want to know there are 4 hearts out of 52 cards, right? There are 4 hearts out of 52 cards. But if you're going to do without replacement, you throw cards out, you remove them. That's the countdown. Okay, so let's say that you've drawn the first card and it's a heart. Okay, how many cards are left in the deck? Not 52, but how many? If you've drawn a card already, it's no longer 52. It's going to be 51, right? If you've already drawn a card out, you're leaving it out. You have 51 cards left. Now, I'm assuming that the first card we've drawn is a heart, right? It's like we're winning a game. We need that first card to be a heart. Now, if you've drawn a heart, there are 4 hearts. If you've drawn out a heart on the first card, how many hearts are remaining in the deck for the third draw? We have 3 remaining, right? So that's a probability. So basically, 4 over 52, that's a probability of getting a heart on the first draw. This, 3 over 51, that's a probability of getting a heart on the second draw, given that, remember, conditional probability. Given that you got a heart on the first draw. That's conditional probabilities. All right, correct. And then given that the first 2 are hearts, What's the probability the third is a heart? Very good. 2 over 50. I'll type it out. Now, you don't have to do this on your homework, but I think it's nice if you want to get a better understanding. Okay, so what's the 2 over 50? It is the probability that the third card, I should have said, the probability that you get a heart on the third card, given that you get a heart on the first and a heart on the second. I'm not requiring you to write all of that out, although if it helped your learning, feel free to write that out. Okay, but that's why. We're building up the scenario, right? You're conditioning on the prior events. Any questions? Yeah, that was one of the trickier computations, right? And then you multiply fractions across and so forth. Any questions? Any questions? I'll wait another minute. And again, if you want me to stop recording, go ahead and tell me or chat at me to stop recording. Otherwise, students find this useful. You're very welcome. Yeah, students do find these recordings to be useful. Okay, any questions? Again, thank you for your hard work and your commitment. Any questions or wait up? Okay, another 15 seconds. Any takers? All right, so any takers? I will see you Wednesday, if not for office hours before. Take care, everyone. Take care. Thank you.